Okay, this is your last homework. The due date is 1 week from today. There are 3 problems. Um, okay. Probably by now you forgot, what you learned before because we didn't have classes for a week. So let me review briefly what we were trying to do. So we started talk about wave structure interaction when you have some structure in waves. Okay. So there is an incident wave train, and at this point, we assume there is only one wave frequency, and then there is a wave amplitude. Once you specify wave frequency, wavelength is determined from a linear dispersion relation, and also the other dependent parameter is a wave amplitude. And when incident wave train approaches a body, and then you expect some waves will be reflected. Some waves will be reflected. So these are the reflected waves. Reflected waves because there is a body, and some waves will be transmitted because it's not completely blocked. So reflected waves travel to the left, and the transmitted waves travel to the right. Okay. And at the same time, this body starts to move once the wave train hits the body, and therefore the body will generate waves by its own motion, and these are the radiated waves. They move outward, away from the body. Okay, this is the whole system that we have, and so in general you have to solve whole problem, but under linearization, meaning that the wave amplitude with respect to wavelength is much less than 1. Okay. So this is wave amplitude and this is wavelength. So if the length of body is about 100 meters, then you're typically interested in waves of wavelength of 100 meters. And then if amplitude is 1 meter, then this ratio is much less than 1. And then you can do the linearization, okay, right? That's what we talked about, linear waves. And if we assume that, then the motion of the body will be small as well, and therefore we can use a linear theory. And under the linear theory, we can decompose the whole problem into 2 problems. One is radiation problem, and the other is diffraction problem. So here, let me write diffraction problem first. So this is diffraction problem. So this is diffraction problem, and this is radiation problem. So the whole problem is considered as a linear superposition of two different problems. And diffraction problem is the problem with a fixed body. So you assume the body is fixed. So body is not you hold the body, and then you have incident waves. And then you have reflected and transmitted waves. So this is reflected waves, and this is transmitted wave. Okay. So since the body is fixed, there is no radiated waves because you are holding it. So you have a structure, fixed structure, and waves are coming, and some waves will be reflected, some waves will be transmitted. And radiation problem, on the other hand, there is no incident waves. And we assume body start to move with some excitation force, and then this guy is in motion. Okay. And then you generate waves. So these are radiated waves. Okay. So when you combine these two, that's exactly what you're looking at here. Okay. And but you can do this decomposition because you assume the incident wave amplitude is much smaller than wavelength, and therefore the motion itself is small as well. Okay. So under that linear assumption, you can do this decomposition. Mathematically, after we linearize the problem, we solve Laplace equation with a free surface boundary condition. This has to be imposed at z equal to 0. That's what we talked about. And then we need a boundary condition on the body boundary, which is d phi dn is v dot n. Okay? So this is the velocity of the body on body surface. In general, the body is in motion, so the position of body is time dependent. But for linear assumption, we assume the motion of the body is small because the amplitude of incident waves is small, and therefore instead of imposing body boundary condition at the instantaneous position of the body, we impose body boundary condition at the mean position. Okay, so when I put 0, that means this is the mean position. So body position changes, right? If you think of a hip, and this guy, keeps moving up and down, and therefore the position of the body, where we have to impose body boundary condition, will change. But since this variation amplitude is so small, okay, and therefore instead of imposing body boundary condition at the instantaneous position, we impose boundary condition at the mean position. Just like, we impose free surface boundary condition. Instead of, here, we impose free surface boundary condition at the mean position. Okay? Just like that, body boundary, we do exactly the same thing for the body boundary condition. And then we have a boundary condition at infinity. Okay, so our coordinate system is like that. And then we need some radiation condition. As r goes to infinity. Okay. So this is a setup that we have to solve. But since we decompose the problem into two, we can write phi as a two component, And one is the radiation potential, and the other is diffraction potential, or diffraction potential plus the radiation potential. But for diffraction potential, we need the incident waves, which is known. As I said, once I specify wave period and wave amplitude, I can specify the incident waves, right? So I need an incident wave. This is known. And then we have a reflected waves and transmitted waves, which we call diffraction, which can be represented by this diffraction potential. Okay? And then for this problem, radiation problem, we need the radiation potential phi r. So these are two unknowns that we have to find. The reason why we do this is from here. So we substitute this guy into here, then what you figure out is the following. So body boundary condition with this decomposition is right? And then I move, the d phi di, which is known, to the right-hand side with a negative sign, with I here, plus v dot n. This is, we assume this is known, how the body moves, although we'll find it later, but at this point, we just assume this is known, and then this is known because we specify amplitude and frequency, and then because this is a linear problem, I can say diffraction potential satisfies this, and radiation potential satisfies this. Okay? This implies this. So if I find phi d, phi r such that phi d satisfies this boundary condition and phi r satisfies this boundary condition, then the original body boundary condition is satisfied. Of course, we impose body boundary condition at the mean position. Okay? So for this, since we separately impose boundary conditions for phi d and phi r, we decompose total velocity potential in this way. But both phi d and phi r will satisfy this guy and this guy and this guy. Okay? So both d and r will satisfy the Laplace equation, and this is true, and then and some radiation condition that I have to impose for a radiation problem. So basically, the only difference that we have to impose for radiation condition. The only difference appears here, okay, between phi d and phi r. So the mathematical or numerical method to solve this boundary value problem for phi d and phi r are identical, okay, and as you will see a little later. But once you once you solve this boundary value problem with these boundary conditions, then you have a velocity potential, and then you can compute hydrodynamic pressure. P, of course, is linearized because we linearize the problem, okay? sometimes, people compute, the nonlinear pressure as well, but that is not quite consistent with the original assumption. If you want to include the nonlinear pressure, then you have to compute, the nonlinear boundary value problem. Here we already linearize the problem because we're using linear free surface boundary condition, and therefore, to be consistent, we have to use just linear representation of hydrodynamic pressure, okay? And then we can substitute, that decomposition here, okay? Minus rho d phi I dt. No, not I, R dt. Right? So far so good. And then hydrodynamic pressure force is just integration of pressure after you multiply by normal vector, then you will get a force. And you have to integrate, the pressure over hydrodynamic pressure over the surface, and then here we integrate over mean surface instead of instantaneous position of the body surface to be consistent with everything. Here we impose body boundary condition on the mean position. Okay, and when you put that this expression for pressure here, then I end up with rho d phi I dt plus d phi d dt. And then normal ds. Since I'm integrating over the mean position, this n is a normal vector toward the body, always away from the fluid, right? And so this normal vector is defined on the mean position of the body. Actually, normal vector changes in time if this guy does, rotational motion, okay? Translational motion doesn't change, the normal vector. But if this guy is rotate, and then if you use, the instantaneous position, then the mean position has to change in time. But if you use, mean position, then this guy is independent of time. It only depends on geometry. Okay. And this part of force is called the, wave exciting force. Or wave excitation force. Something like that. And this part is radiation force, which we call, okay? And as you will see later, this term, this force gives, eddy mass and the wave damping term. Okay. I will show you how we get that. But this radiation force gives eddy mass and wave damping, and then. And what else? Oh, of course, the final goal here is to determine the motion of the body when waves, approach to the body. Okay, that's our final goal. So at the end, we have to solve, the equation of motion for the body, right? So to do that, not only we need a hydrodynamic force, we need a hydrostatic force as well. So hydrostatic force is hydrostatic pressure times the static pressure. All right. And which is minus rho g z and the s. Okay. So that can be written as V dV. This is Gauss theorem. So something like you have some function normal ds that can be changed to, right? This is Gauss theorem. So that's exactly what I'm doing here, going from here to here. I'm using this guy. So F is rho gz, but rho and g are constant, so I pull out, and this F is nothing but z. And then you can see this guy is obviously has a unit vector in the z direction. So okay. Which is nothing but buoyancy. Okay. But one thing that I want to point out is here, I didn't use 0 here, not here. I just use S of B instead of SV not. So in other words, I integrate this static pressure over instantaneous instantaneous position instead of mean position. Okay. The reason is this guy is order 1 quantity. Here, this guy is small because the wave amplitude is small. The velocity potential associated with the wave amplitude is small as well. And this is small, therefore the diffraction and radiation potentials are also small because that is due to the small amplitude waves. And therefore we assume these are small, and this is small. And therefore we multiply by order 1 quantity. Okay, then it's small. Here, this is order 1 quantity. So here we have not only order 1 quantity, but also order epsilon quantity as well. So just think about it. This is my mean position of my box, and this guy is moving, going up and down, and then this. So this part is SB naught, and this whole thing is SB without 0 here, okay? And this difference is due to the motion of the body, which is the motion of the amplitude of motion is comparable to the amplitude of incident waves, okay? So here I include order 1 part plus, let me call this part is delta S. So delta SB is SB naught plus delta SB, okay? So this part is due to the motion of the body, and so I'm including both. Then this guy has not only order 1 quantity, but also the order epsilon quantity as well. So if you want, I can decompose this guy as this. Linearization again. Little messy here. So this is an equilibrium. I'm sorry. This is a buoyancy in equilibrium, which is balanced with the weight of the body, and this is the additional static force due to the motion of the body. Okay. So this part is really what I need. So I called F static. Let's call it S. Okay. So from there, we can write the equation of motion. Which says, the mass times, acceleration, let's call x, has to be balanced with the force applied to the body. So the first part is excitation force, and the second part is radiation. I call R, the radiation force, and then we have a static force as well. Okay. So that's what we have to solve later, and we'll find out what this, and what this from now on. Okay. So I haven't discussed how we get the details of how we get radiation potential, diffraction potential, and so on. But once you learn those things, then you can compute force, and then you can write the equation of motion over there, and then you can find the motion of the body for given wave amplitude and frequency. And likewise, the moment can be computed as this. And once again, I integrate this part over the mean position. So this x, which is the motion of the body. But let me use capital X of the body. Okay, that's what we are trying to find out. Okay. So at this point, you should be clear about the decomposition, radiation, what is the radiation problem and what is diffraction problem. And then the other thing that you have to clear about is, why we are doing that and how we construct, the equation of motion, okay? And so from now on, what we are going to do is we discuss, how we solve this boundary value problem and what kind of terms we will get from here. Any questions so far? Okay. Then let's talk about how we solve this boundary value problem. But I want to, make an emphasis on the following. We could do this decomposition because we assume we have linear waves, and therefore we could do the linearization. If waves are large, or the motion of the body is large, then we cannot make this decomposition. Okay, then you have to solve everything together with nonlinear with the nonlinear free surface boundary conditions and so on. And at that time, we cannot really do the decomposition like this. We have just force on the right-hand side. Okay, that's it. Then you have to solve this part. Of course, finding this is difficult because you solve a nonlinear problem. But suppose you could do it, then after that, what you need to do is solve this problem. But this time, since we did a linearization, we can decompose into this way. And furthermore, as you will see soon, these have this, particularly this and this one, have simple forms, so that we can write the linear equation of motion, which is familiar to you. Okay. So now, to solve this, as I said, the governing equation is the Laplace equation for both, diffraction and radiation problem, and the free surface boundary condition is exactly the same, and so on. So we use, similar method to solve, this two boundary value problem. But first, notice that phi I is proportional to e to the minus I omega t. Okay? Just in case you don't remember what this guy is, phi I is, if I remember correctly, is something like this. Infinity is deep order. Okay? For finite depth, this guy has to be replaced by hyperbolic cosine function. But in infinite depth case, this is the velocity potential for incident waves, and therefore phi I is proportional to e to the minus I omega t. Okay. So something is periodic in time, and therefore we can imagine phi d and phi r are proportional to e to the minus I omega t. Okay? So think about it. Incident waves are coming with this frequency, e to the I omega t. And then reflected waves will have exactly the same frequency, and the transmitted wave also will have that frequency. So this guy will generate waves with this time dependence. And in addition to that, once the incident waves hit the body, then body starts to move. And the frequency of the body motion is exactly this frequency, if it is linear. If it is nonlinear, then even though you have only one frequency coming, this guy doesn't have to move with that frequency. Okay? But if it is linear, then this guy is moving with that frequency. So because of that, radiated waves will be also proportional to e to the minus I omega t. So this is a very natural to think this way, and therefore we write phi I dr in the following way. Okay? And of course, in this guy, it depends on x and z. In 2D problem, in 3D problem, it will depend on x, y, and z. Okay? So basically, what I did is I pull out time dependency from the representation of velocity potential. This is not true for nonlinear problem, as I said. Also, this is not true even for linear problem if you are interested in transient motion. As soon as there was incident wave hit the body, you wouldn't see this. It's more complicated time dependency. But once transient motion dies out, so if you wait a little longer, then this guy will move with the same frequency as this guy. Okay? So if that is the case, then we can write the solution in this way, and then still this is true, right? Because there is no time dependency. But if I look at the free surface boundary condition, then I realize that I can write no. So once I assume the velocity potential is proportional to this e to the minus I omega t, then we write this, and then there is no time dependency here. But you see the frequency omega, so this is frequency domain approach. So if someone says, I solve, the radiation problem in frequency domain, which means, you assume the velocity potential is proportional to e to the minus I omega t, and then this is a boundary value problem that you have to solve. Okay. And boundary condition, body boundary condition. And then for phi d, I still can do this. Okay. First of all, the normal vector this means, right? That's what it means. Gradient of phi d dot n. And here, I pull out time dependence like that. And this is independent of time because we impose this on mean position. As I said, once you fix, the body, then the normal vector doesn't change in time. So this is independent of time, and this is independent of time because, I pull out the time dependency here, and therefore, the body boundary condition for this guy can be written in this way. Okay? Still, I don't have a time dependency. So you combine this and this, and then you solve the diffraction problem. Okay? So this is for diffraction problem. So this is body boundary condition for the diffraction problem. Yeah. Thank you. I need a minus sign here. In addition to that, this phi I is proportional to wave amplitude A. So if you want, you can pull out A as well. So you are looking at velocity diffraction potential for unit amplitude. You can do that. Once you find the phi D, then you can multiply by wave amplitude. But I'm not going to do that at this point. But I just want to point that out. But okay, let me write that down. Right-hand side is proportional to wave amplitude. Okay, phi I is proportional to wave amplitude. Okay. And at the same time, for radiation problem, so this is for phi D. For phi R, I have d phi. Let me start from here. D phi R dn e to the minus I omega t, right? That's the left-hand side. And the right-hand side is v dot n. And the v is, let's put, because body is moving with that frequency, that's why we could pull out this. And therefore, we have v dot n e to the minus I omega t. And this guy is independent of time. And so that is, only a function of space. So we can drop that, and then at the end I have a d phi r dn is equal to v dot n. So with this, representation. Okay. So this v is capital V here. This is a vector. I haven't written, what v is in terms of the motion of body, but I will do it, so. But so this is a body boundary condition for the radiation problem. For the radiation problem. Okay? Okay, what else? So now we have a boundary value problem which is independent of time. It only depends on frequency and the amplitude, of course. And so we from now on we solve the problem in the frequency domain instead of time domain. Okay. But if you are interested in transient motion, or if you have to solve nonlinear problem, then you have to solve in the time domain instead of in the frequency domain. Okay. And if time domain, to solve this problem, you need the initial condition. So here, the radiation condition, to be more specific, says waves basically are propagating outward, meaning that the waves are always propagating away from the body. Okay. As I mentioned, last time, if you solve the mathematical problem, you see waves are coming toward, the body as well, and that is not physical because, there is no energy source to generate, waves coming from infinity, except, incident waves. So if you pull out incident waves, and other than incident waves, there is no there are no waves coming toward the body. Okay. So now, except this part, this is very similar, except in this and this actually. Problem is very similar to the problem that you solve in unbounded domain, okay, using panel method. Okay. So for unbounded domain, you solve something like this, right? Then for 2D, for two-dimensional unbounded domain, you solve this by using distribution of sources. Okay. Do you remember this? This is a two-dimensional source potential. We distribute the sources along the body, and then of course to determine strength, we use the panel method, right, to compute strengths of sources, and then you can compute velocity potential everywhere. Now, so G is we call Green function, right? And this Green function satisfies the Laplace equation and satisfies this condition at infinity. The only boundary condition that this Green function doesn't satisfy is the body boundary condition, right? Therefore, what we did is what we impose body boundary condition to determine Q. then this velocity potential satisfies, carbonization and boundary conditions. And also this guy is a function of x. Okay. So we integrate over x prime. That's why I put prime here along the body surface. Okay. And then you get a function of x. So if you look at this guy and this guy, it's very similar, except this and these two, this and this, free surface boundary condition and radiation condition. So what we are trying to do, we write the solution exactly the same way. So for example, diffraction problem or radiation problem, what we do is we write the solution exactly the same way. This time mean position. Okay. And I want to make this velocity potential satisfies this whole thing, except body boundary condition. Okay. So this guy G will find G such that satisfies the Laplace equation, except x is x prime. As we can see here, if x is equal to x prime, this guy blows up, and therefore it doesn't have any meaning. But if x is not equal to x prime, then this satisfies the Laplace equation. Just like that, we find a Green function in that way, and also we find the dg minus, let me remember this way, at z equal to 0, and then we have and radiation condition. So as you can see, G satisfies carbonization and all boundary conditions except body boundary condition. Okay? So you can imagine this G will be more complicated than this. Here I didn't have this. Okay, I didn't have that. Now I have this and that. So G will be basically 1 over 2 pi log like that, plus something else which we have to find. Okay. Without that, without H, this guy doesn't satisfy the free surface boundary condition and radiation condition. Okay. This guy doesn't represent any wave motion, and therefore we need that. Finding H is not, it's definitely doable, but it's not that easy. Okay. And once you find the H, what you need to do is impose a body boundary condition. So now, next step is first find the Green function, and the second step is to find Q by imposing body boundary condition. For both radiation and diffraction problem, you have normal derivative of velocity potential is equal to something that we know. diffraction problem, this is an incident wave potential. And radiation problem, this is a body motion, which we assume we know. So, therefore, we impose body boundary condition here. And then this could be either D or R. And then we end up with I have a minus sign, right? In 2D. So when I substitute this guy into here, and then this is a singular part, and this part is regular, and this is singular. Both satisfy Laplace equation, okay? But this guy is a regular, meaning that there is no blow up. Even though x is x equal to x prime, this guy has to be bounded, and therefore I don't have to worry about x prime. X approaches the body surface. Okay, so that's why I didn't do anything for this term. But here I have to worry about x approaches to x prime. X prime is on the body. Okay, then we talked about how we pull out the contribution. As x approaches to x, how we pull out, that contribution. That's what we discussed, when we talked about panel method. And so this part gives these two terms. This is a principal value type interval, and then this is regular. And now you can evaluate this guy and this guy by using, panel method, and then this is known, and therefore you can determine Q. Okay? For example, using determine Q, for example, using the panel method. With that we discussed. Okay. I haven't written what is H yet. Okay. But H is introduced for free surface boundary condition to be satisfied, along with the radiation condition. But that is regular, so I don't have any trouble in integrating this or approximating this for a numerical method. But this guy is a singular at x equal to x prime. That's why I have to make a special treatment to write this way. But once you do that, then this is known because right hand side of this part is unknown. This is known, and we assume this is known, and therefore this is known, and therefore the only unknown is Q. And you can construct the matrix as before, and then you can solve it. Okay? So that's the idea of solving, radiation and diffraction problem. So once you find, phi, then we can compute, the hydrodynamic pressure. And then, as I said, you integrate, pressure, then you can get the, force, and then you can set the, you have a equation of motion. Okay. By solving that, you will get the motion of the body for given wave amplitude and frequency. To give you a little idea of what this term looks like, okay. In this class, and I'm not going to talk about how we get this, okay. But I give you some form that for 2D problem. So for 2D, you can do exactly the same thing for 3D as well. G is, as I said, 1 over 2 pi log R. So R is, right? And then I have to write H, which is the following. Okay? So this is a Green function for a two-dimensional problem. So this Green function satisfies Laplace equation and the free surface boundary condition and the boundary condition at infinity and radiation condition, meaning the waves are always propagate outward. and this H is the expression inside of this, the dotted circle is really H. How do we get, H? We get that H, by taking, the Fourier transform of this problem. Okay, but it's a little lengthy, and at this point, I don't, want to go through. And there is a book which is available on website, right? I give this reference. If you look at this book, and then this book has all the the expressions for green function, 2D, 3D, time dependent, and or not. Okay. So you can take a look at that book, and on syllabus, I gave a specific reference of this book, okay, and which is available online. We can download in a PDF file actually. So if you look at that, then you learn how to get this, and so on. And here, this is the once again principal value integral over small k, and which will then you have a this will be a function of a capital K and x and z, and capital K is nothing but wave number associated with the frequency, okay, through the linear dispersion relation for infinity deep order. So once you evaluate this, you have to evaluate this numerically, okay? There's no analytic expression for that. So you have to integrate this numerically first to evaluate G. Once you have a G and then an H, then you know this numerically, and then you do the numerical integration of this guy as well to determine Q. Okay. So the first step is to evaluate H numerically, and then plug in here, construct a matrix, and then determine Q. So finally you will get something like is right hand side, right? So here Q will be I goes from 1 to number all the way to the end, which is number of panels that you have, and then you can construct this, and then you determine Q. Once you know Q, then you can write the enclosed potential, and then you evaluate the pressure and the force and so on. If you know a little more about this, I think the Dr. Hong from Moeri will offer a class in fall 2011, this fall, and he has a lot of experience of working on this. So if you're interested in learning more about this and more practical application and so on, that could be a good class to take. But I think for this class, solving diffraction, in terms of solving diffraction and radiation problem, this is good enough, okay? And then I'm not going to talk more about how we get this and how to solve this, okay? So at this point, I assume you know how to solve this, and then I'll continue, okay? I mean, there are a lot of details that you have to learn if you really want to, program everything, okay? And so it depends on, your research area. If you are really working on this, and then of course you have to learn, many things. But if you're not, if you don't want to be a hydrodynamicist, and then you typically use code that is already written. Okay, so the most of the sea-keeping code or the code to compute hydrodynamic wave forces uses the method that I described here. Okay, but there are a lot of details that you have to know if you want to write the code by yourself. But this is a well-developed field, and so there are many codes available. Okay, but you have to know, what the code does at NIST, even though you don't know the details, right? So at NIST, you should understand, what I'm describing here, and to know what is going on inside of the code. If you don't know anything like this, then code is really black box. Okay, and then even though you see some output, you don't know what you're looking at. All right. So at this point, I assume you know all the procedure, even though you don't know the details. Okay, how we decompose and how we get the formulate the boundary value problem and what kind of method you can use and so on. Right? Okay, and after that, I'll talk a little bit more about the radiation problem. Okay, and I said once you solve this, you will get a radiation potential, and then from there you can get a radiation force. And earlier I said radiation force can be decomposed into eddy mass part and the wave damping part, which is not clear from here. Okay, so I'll talk about that connection. How once you solve radiation problem, how you get the eddy mass and how you get the wave damping term, and then how you write the linear equation of motion. So that's what I'm going to talk about the next Tuesday. Okay, and then after that I will review the material that we discussed, and next Thursday I asked Seongjin, who works with me, to give a small lecture about his dissertation work, where he solved the radiation diffraction problems with a submerged body. Okay, so you will learn what you will end up with when you solve these problems, and particularly in the time domain, not in the frequency domain. And in addition to that, he included in a nonlinear term, and so what kind of a nonlinear force you will get. So you'll get some idea of what you can do beyond what I described in class. Okay, so that's the plan for the next week, and after that we'll take a final, and that could be the end of the semester. Okay, all right.